This is section 4.6b, graphs of other trigonometric functions. So yesterday we did graphs of tangent and cotangent functions, and today we're going to do the secant and cosecant functions. Graph of the parent cosecant function. Sometimes it's pronounced cosecant. You can say it however you want. The way that the graph of the cosecant function is you can tell that it's very much related to the sine curve. In fact, often when the cosecant curve is pictured, it's pictured with the corresponding sine curve in gray on the same set of axes. Now the reason for that, of course, is that the cosecant of x is simply 1 over sine of x, since the cosecant is the reciprocal function. And that's why the easy thing about graphing cosecant and secant functions is that once you have the corresponding sine or cosine, it's just a matter of connecting curves that touch those sine or cosine curves. And we'll see what that means in just a bit. For now, let's look at some of the basic characteristics of the cosecant. We have the period, 2 pi, just as you would expect, because that's also the period of the sine. Domain, all x, that's not equal to n pi, and that's because we have asymptotes at all multiples of pi. Now, the reason for that is if the value of the sine function is 0, well then obviously 1 over 0 is undefined, and that's why we have asymptotes there. The range is from negative infinity to negative 1, union 1 to infinity. We can see that clearly from this graph. Vertical asymptotes, as said a little bit ago, it's those correspond to the numbers that are not in the domain. And finally, the cosecant function is odd because cosecant negative theta equals negative cosecant theta. And that, of course, means that the graph of the cosecant function, just as the graph of the sine function, is symmetric about the origin. How to graph the cosecant function? Alright, to graph y equals cosecant x, use the identity cosecant x equals 1 over sine x. So what you do is you look at the values for which sine x equals 0, and you remember that you have asymptotes there. Properties of y equals cosecant x. Domain all real x such that x is not equal to k pi. This is what the parent sine function looks like, and that's always a point of reference when we're gonna graph the corresponding cosecant function. This is what the cosecant function would look like. See how its vertices touch the peaks and troughs of the sine function, and also the asymptotes occur at multiples of n pi. The range is negative infinity to negative 1 and 1 to infinity, periods 2 pi. And we can use dotted lines for asymptotes as we normally do at the multiples of pi. Now, just to confirm that visually, notice that at the multiples of pi, so I'm talking about negative pi, 0, pi, 2 pi, 3 pi, 4 pi, and so on. At all of those multiples of pi, notice that the sine function crosses the x-axis, which means that there's a y-coordinate of 0. And 1 over 0 is undefined, therefore we have vertical asymptotes there. Now let's look at the graph of the parent secant function. As you can see, it's also very similar. The secant function always has a corresponding cosine function because the secant of x is 1 over the cosine of x. The secant of x is the reciprocal function of the cosine. Characteristics are also similar to the cosecant graph. Period is 2 pi. Domain all x not equal to pi over 2 plus n pi. Range negative infinity to negative 1, 1 infinity, 1 to infinity. And the vertical asymptotes occur at the multiples of pi that are added to pi over 2. Now, again, it's the reason we have asymptotes. It's the same exact reason as we had for the cosecant graphs. It's because 1 over 0 is undefined. And finally, secant of negative theta equals secant theta. The secant function is even. All right, so up until now, we've seen six trigonometric functions, and each one of them is odd or even. And so far, you may have noticed that all of the trigonometric functions, except for 2, all of them except for 2 are odd. The only 2 even ones are the cosine and the secant. And just a quick review about what an even function means. Just as an odd function is symmetric about the origin, an even function is symmetric about the y-axis. How to graph the secant function. To graph y equals secant x, use the identity secant x equals 1 over cosine x. Values of x for which cosine x equals 0, the secant function is undefined, and this graph has vertical asymptotes. So let's look at the properties of y equals secant x just as we did for the properties of y equals cosecant x. Domain all real x such that x is not equal to k pi plus pi over 2. You don't have to worry about that if it looks confusing, because once you graph it becomes pretty apparent. Let's look at the graph of y equals cosine x and compare it to the graph of y equals secant x. You can see once again, just as we did with sine and cosecant, that the graph of the secant, the vertices of the secant graph, touch or are tangent to the peaks and troughs of the cosine graph. The range is the same, negative infinity to negative 1, union 1 to infinity. Period is the same, 2 pi. And vertical asymptotes occur at multiples of pi that are added to pi over 2. We can see that clearly because at all of those numbers, pi over 2, 3 pi over 2, 5 pi over 2, etc., the value of the cosine function is 0, and therefore 1 over 0 is undefined. Elements of child cosecant and secant functions. You're going to recognize that this chart is very similar to the tangent and cotangent functions, and also, of course, very similar to the sine and cosine functions. We have our elements D, A, B, and C. D is vertical shift, A is vertical stretch or shrink. B affects the period because period equals 2 pi over B, so that gives us horizontal stretch or shrink. And C and B together determine our horizontal shift. C over B is our horizontal shift. Now, since cosecant and secant functions have a start angle of 0, just as the sine and cosine, well then, finding the horizontal shift is equivalent to finding the start angle. And that's something that we saw in section 4.5. Example, graph y equals 1 plus 1/2 cosecant 2/3 x plus pi over 3. So how are we going to attack this problem? Well, you'll notice that your calculator doesn't have a cosecant button, but you can probably figure out a way to write all of this in terms of sine. You could do that. But the point of this lesson and previous lessons is to learn the math behind the curves and to learn how to graph them by hand. So the strategy is, first graph y equals 1 plus 1/2 sine 2/3 x plus pi over 3. Then draw asymptotes where necessary and add cosecant curves. So the trick in graphing secant and cosecant curves is to graph the corresponding sine and cosine curves, because once you do, it's really just a matter of making sure that the vertices touch the peaks and troughs and making sure that you draw the asymptotes in the right places. Continuing the same example then, we're going to graph y equals 1 plus 1/2 cosecant 2/3 x plus pi over 3. So without graphing yet, I'd like you to pause the video, figure out what you can just from the equation, put it all in terms of A, B, C, and D, and get your start angle and horizontal shifts, etc. and then resume when you have that information. Okay, so here's what we can tell just from looking at the equation. We have a vertical shift of 1, our d is 1. We have a vertical shrink of 1/2, because our a is 1/2. Period is 2 pi over b, and since b is 2/3, 2 pi divided by 2/3 equals 3 pi. And a horizontal shift, which for sine, cosine, secant, and cosecant all always coincides with the start angle. Or horizontal shift and start angle is negative pi over 3 over 2/3. Where do we get that? Because remember that we're talking about c over b. And since the standard form is minus c, well, plus pi over 3 is the same thing as minus negative pi over 3. And so our c is negative pi over 3. Therefore, c over b is negative pi over 3 over 2/3. And that, of course, simplifies to negative pi over 2. Okay, so at this point, you know that you want to set up your chart, graph your 5 critical points. So pause the video again, set up your chart, and then resume when you have your chart. Here's what the chart looks like. In our x row, we have, of course, our starting angle, negative pi over 2, which coincides with our left shift. And then since we already found out that the period is 3 pi, then we know how much each quarter period is worth. Each quarter period is worth 3 pi over 4. And so if you add 3 pi over 4 to negative pi over 2, of course you get pi over 4. You add 3 pi over 4 to pi over 4, you get pi. Add 3 pi over 4 to pi, you get 7 pi over 4. And add 3 pi over 4 to 7 pi over 4, and you get 5 pi over 2. So we've got our critical x coordinates, and then to get the y coordinates, we simply plug each of those values in to 1 plus 1/2 sine 2/3 x plus pi over 3. And you can do that on your calculator. You'll get 1, 1.5, 1, 0.5, and 1. So we now have our 5 critical points. So the last checkpoint is what you're going to do now is you're going to pause the video, graph these points, and remember what you're graphing first is the sine function, and then try your first graph of the cosecant function, which always uses the sine as a point of reference. So pause the video, graph this on your own, and then resume when you have a graph. So first, of course, you plot the points. Negative pi over 2, 1, pi over 4, 1.5, pi 1, 7 pi over 4, 0.5, and 5 pi over 2, 1. And the last step is connect the dots and fill in the curves and the asymptotes. And this is the correct graph. This is the correct graph. Classwork, page 339. Please write these numbers down and see you in class.